Hello. Today, for the course on differential graded categories, we will deal with the homotopy category of a strongly pretriangulated digi category. So, recall digi category A is strongly pretriangulated if, essentially it has shifts and cones internally, and in the end you will obtain these sequences if you start with some closed degree zero morphism. We have these sequences, so-called pretriangles. They are like if you want, the internal version of the pretriangles we know in the DG category of DG modules, and shifts and cones are understood via representability. This is very important. This is a key feature, key aspect. Namely, for example, the shift, this object, comes with an isomorphism. So this, as DG modules, and whereas the cone satisfies this, well, or even more precisely, I should say that the cone, and this is also important, the cone is this object together with this isomorphism, as the shift is this object together with this isomorphism. And then you know that by the Yoneda lemma you can also describe this isomorphism completely by means of some element. For example, here, this element we called this completely describes the isomorphism. So you should know that you can express this isomorphism alternatively in terms of this element, for example, for the shift, but I mean also for the cone. You have your pair of elements. You have a pair of morphisms from the cone to this and to this, and then you have these elements and a universal property. If you want, I can say this via a universal property. And this we discussed last time. Okay, what we are interested to do today is something a little different. Namely, we will take a look. So what happens in the homotopy category, or more precisely, what happens in the homotopy category with respect the pretriangles. Well, it turns out that one can prove some interesting, useful properties about these pretriangles. So if you want about shifts and cones, just reasoning inside this homotopy category. So now, from now on, we will always fix a pretriangulated DG category A, and set, we call T, well, this T has a reason, this choice of name has a reason. It's like stands for, like a little spoiler, this stands for triangulated. Okay, and just a caveat, we will mostly work inside T. So, for example, with morphisms, for example, F from A to B in T. Be careful that, F as a morphism in T is actually a cohomology class, but sometimes we will drop the reference, and some other times we will need a reference to some representative of the cohomology class. So we'll have this little, I hope, abuse of notation. Just be careful. Depending on the context, we will deal with, like, use this notation. F will be itself a cohomology class, but sometimes it will refer to some representative of its cohomology class. And so sometimes we will still need to work inside here with some, like, actual morphisms and not classes, not morphisms in the homotopy category. Okay, so first we have to discuss shifts. And we have this result, can write it, lemma. Of course, you can map. It's strongly pretriangulated, so like you can do this. Like you can try and map an object with n shift, but the important thing is that this can be promoted. Can be promoted to a k-linear. K is our base field, a base commutative ring. We fixed it like in the very beginning of this course. So what we have is actually a functor from T to itself, and this works for every integer. And there is something more to be said, namely that if you take this functor from n equal to 1 and the other with n equal to -1, these are essentially inverse to each other. In the sense that there are isomorphisms in the functor category, which we should know about, I hope. So you have the identity functor, and this is isomorphic of composing -1 and 1, but also this. There are, if you want, autoequivalences. Just let me just recall what it means for like f in general, f and g to be isomorphic as functors, if you want, from t to t, means that we have some family of isomorphisms and you have compatibility. This is phi b, and this is for every f of f, g of f. This is going to be commutative for all morphisms. So it's a natural transformation. We don't have signs here because we're working with k-linear categories. And it's a term-wise isomorphism that we should know, just a short reminder. And moreover, we also this, let it here, and moreover, we have for if you want n integer but positive, we have isomorphisms of this type. So you can n shift, it's like just the composition of the shift by 1 n times, and you can expect that the minus n will be the same thing, but yeah, it's what you would expect. Okay, good. So let's prove this. So we want a functor. From t to t. So we know how to define it on objects. It's the shift inside, it's pretriangulated DG category. The n shift is an object in the DG category, so of course it's an object in the homotopy category, which has the same objects of your given DG category. So we just need to, if you have a morphism, in T, we want to define some n shift of the morphism itself, and of course this has to be functorial. In particular, we will want that if you the identity on the n shift is going to be the shift of the identity, and also compatible with compositions. These are G and F are composable morphisms. I'm just not specifying which objects. So how do we do this? The strategy. This will be essentially the key argument of this whole lecture. The strategy is always to use representability. So the idea is we know that n shifts are representing objects of some module, and within modules we are kind of working with complexes, at least object-wise complexes, and shifts are well understood there. They're just shifts of complexes, object-wise, of course. So we will be able to define everything at the level of the G modules, and then using the representability isomorphisms, we will be able to go back and get what we want. So let's do this. Thing is, have to be a little bit careful now because we are working with morphisms in T. be careful just of this. T is H0 of A, but fortunately we have the Yoneda embedding. You take H0 of the Yoneda embedding and you get still something which is fully faithful and still maps A to this. And F from A to B, which is now is itself a cohomology class. This is, if you want, it's well defined as a morphism in H0, and it's fully faithful, so like it has all the nice properties. For example, if this, I mean, just saying, if this is an isomorphism, this will be an isomorphism, and so on. So we can just, essentially we can use this Yoneda embedding viewed like after taking the H0 and like work here with this. Indeed, yes, you consider, for example, I mean, this F is mapped here, so we know this N shift at this level, and I mean, this is not, I mean, defining this is kind of trivial because like these are really concrete shifts, so and these are like term-wise, they're just complexes. So here what you do is like you shift the degrees. N means on the left, I think, of N steps. And same thing here, but I mean, like since you're shifting with the same N here and here, like the shift of this morphism is just like the morphism itself, but with some, like with the shifted degrees. I mean, it's kind of trivial, and it's even, I think it's for shifts, it's even more complicated to write it down and to describe it than just like than what it is really. I mean, it's, you're doing practically nothing. You're just shifting degrees, and this F shifted by N is just sorry, F itself, but viewed like with shifted degrees. So there's nothing strange here. We definitely know how to do this, and you can check it kind of immediately. I will not do this, but it's really kind of straightforward with shifts. There's nothing much to prove. Indeed, you can see that whenever you take some identity, you take the image through under this Yoneda embedding, and you shift it, then you will get this. And also, in general, you will have this. I mean, actually, there is a point. There is something one should check. Namely, I mean, careful. F, G are morphisms in H0. And like here, like as I said in the beginning, there's some little abuse of notation. I mean, this shift here is actually defined when F is actually just a morphism in A, not a cohomology class. Like here, you take really some morphism of complexes of like the G modules. We have to check that everything does not depend on the choice of representatives. Of cohomology classes, so that indeed the shift is still well defined at this level. When I change the cohomology class, I can change just the cohomology class of F, and like it's going to work. And I mean, think like if you have cohomology classes. So if you want like you may want to prove, for example, practically that, I mean, if f is some d alpha, then f star of n, which is again d alpha star of n, is still coboundary. But this, I think that there's going to be some signs here, but this should be d. So in the end, it will work. You have to do this to check this, but like as said, in the end, it will be okay. Yes, and in the end, these relations will still work at the level of cohomology classes, and then like using the Yoneda embedding, using the fully faithfulness of the Yoneda embedding, you see that indeed, like for example, this is equal to GF star. So in the end, you'll see that you'll get, by going back to using the Yoneda embedding, you'll get these relations. So we are there. We just have to check. I mean, we have this functor. We have defined this functor by means of this representability trick. So you start with something in your category. You apply the Yoneda embedding. You do your constructions there, which are very explicit. You can handle them, and then you use representability to go back. so that in the end you'll get what you want, because I mean you have these isomorphisms. That's the point. Also, I should write them. Like you use these isomorphisms implicitly to go back. Like if you want, you identify this shift at the level of the G modules with this represented DG modules, so that you can go back using these isomorphisms, and everything will work. It's like, I mean, you should try this yourself. I mean, and fill in some details I'm maybe not touching here, but it really works. I mean, it's like a very typical strategy. You want to define some functor internally, as in this case. You apply the Yoneda embedding. You do whatever you need to do inside the G modules, or even the homotopy category of the G modules in this case, and then you use representability. So essentially, you identify this with this. Sometimes it's useful to think these isomorphisms as like really identities, even if they're not. And then you can go back and define what you need, because then you'll get some morphism at this level, something, and then you can like view it as a real map from this to this, and the properties will be satisfied, because the properties at this level of the G modules are satisfied. So I hope I'm clear, but we will see this in action even more times. So I hope that in the end this will sink in. So for example, let's see. Yes. So let's see, for example, how you check the isomorphism. Like for example, this one. So what do we need to prove? Definitely we want some from, let's say, this in this direction. This is from, I mean, I apply -1 first and then +1. I mean, notationally, I mean, this is inverted here because of the way, I mean, shifts they act on the right, whereas normally functors they act on the left. So it is this mismatch here, but no worries. I mean, we will want some isomorphism here, and want also some compatibility of this way. and this will be the... Okay, so how do we do this? Again, we use representability. Okay, why? Because then, like this object, what is this? Like if you want, this is A minus 1, then 1 goes out, and then A, and this minus 1, 1. But like shifting by minus 1 and then by 1 is really, I mean, at the level of the G modules, is really doing nothing. So this, if you want, we can just erase. So, like, I mean, we are already there, because then you have an isomorphism actually from here to here. And by the Yoneda lemma, this gives you some map. Actually some isomorphism, because this is an isomorphism from this to this, from this to this. And what about the representability? I mean, again, the compatibility of this diagram. Well, again, you can prove it. You can prove it. Let's write this here. You can prove it at the level of the G modules, namely you can like apply this. This we have defined somehow. Sorry, this is B, this is F minus 1, 1, and then you take this, and like here, this is F, same thing here. And I mean, this commutes. Like this is commutative at the level of the G modules. Why? I mean, again, have to remember how this is defined. But I mean, this is defined just by means of just using representability. As I said before, right? I mean, you have this. Maybe let's write this even a little more explicit. I mean, if you want. The idea of defining the shift, the n shift, was you have this isomorphism. If you want to think of it as the identity, this you know what it is. This is a shift here. This is an isomorphism. Then you can complete here uniquely, and this is your shift uniquely determined. It comes from a unique map between the objects. So this is the way you understand the n shift internally using this representability trick. And I mean, if you look at this, like the way it's defined, and like it's necessarily commutative. By the very, and the reason is like the very way this is defined. As I said, you can check everything in more detail if you want, but the key thing to remember here is always use representability. Always use representability. And the fact that the Yoneda embedding is fully faithful then allows you to do everything. And like if you want also, it's a good thing, even if it's an abuse of notation, of thinking, at least in some moments, like in sometimes, to think of these isomorphisms, these representability isomorphisms. It's useful to think of them as like actual identities, so that everything is even clearer. Okay, so in the end, I mean, you have this commutativity, and this commutativity will imply this commutativity. So you're there, you're done. And I mean, similar arguments. You produce the other isomorphism, which like is, if you want, this. And also the other isomorphisms, if like here. And I mean, here you will need some induction argument, but I believe that you, I mean, you only use this strategy, and then that should be quite straightforward. You should try it yourself if you want. Okay, so it's good. We have the shifts. We also have natural transformation saying that, I mean, doing a shift of 1 and -1 is the same as doing nothing. And also, like, as I said, like before, like sometimes, like it's good when you have some isomorphism which is natural, like comes from a natural transformation. It will be also good to abuse notation and think of this as an identity. Like, have to be a little bit careful, but sometimes it's really useful, and we'll see it at some point, I think, even today. So we have shifts inside the homotopy category, and this is good. This is good, definitely good. I mean, the thing here, I mean, commutativity here, I mean, I didn't say that, but like this was like in T. Like we defined it in T, and like we are using cohomology. We're using cohomology classes here, and so it's okay. So we have shifts, and now we can make this definition. So let's call it distinguished. In T, what is that? Is a sequence of objects and morphisms in T. We call T, this is the homotopy category of the form okay, with the property that there exists a pretriangle so if you want A prime, B prime, and this is F prime, this is the cone of F prime, and the commutative diagram. Let me write it here. So you can compare these sequences commutative diagram where to be in T this is going to be the shift of U with U, V, W isomorphisms in T. So essentially, what is a distinguished triangle is something, it's a sequence of this form, which is essentially, if you want, isomorphic to a pretriangle. Let's say, even said it better, like it's isomorphic to a sequence which is the image of a pretriangle in the homotopy category A0 of A, which we called T. Okay, so we have these shifts, we have these so-called distinguished triangles, which are essentially the pretriangles, but we allow We allow them also sequences which are isomorphic to them if you want. And then what we're going to do is prove some properties of these pretriangles, which, like, they have some axiomatic names, like, and at the end I will explain more. So first we'll prove this. Which I call TR1. So what you have is an object and a morphism. So first, take the identity, and this is a distinguished triangle, just identity and then 0. And then if you want, F can be completed or embedded into if you want. So you can find some C such that this object such that, and maps such that this is a distinguished triangle. And also 3, this is a little more general, but you VW is to be a commutative diagram in T with UVW isomorphisms then the top row is a distinguished triangle if and only if the bottom row is okay. So essentially, if you want, for this last part, the slogan, distinguished triangles are closed under isomorphisms. Good. So let's give a proof of this. So actually the only non-trivial part is the first one, and let me show you how to do this. So what you can do, we can form a pretriangle in the RDG category. You take the identity, now it's really the strict identity, not just the cohomology cluster of the identity, and then you take the cone of the identity, and then this. I think we actually already used at some point in the previous lecture then like cones of isomorphisms, at least in the G modules, they are contractible. Yes, but I want to give a direct proof here, because that I think the proof we gave back then used some black boxes, and like this today I want to be as self-contained as possible. Actually, the goal of today is that we're building a theory which essentially with which essentially we will be able actually to prove some of that black boxes, even if we'll probably not do that. But like, at least you know that you will be able to prove some of these black boxes if you want. In any case, so let's prove it. Let's see what we can do with a direct proof. And essentially what we want, we can conclude if we show that this cone is isomorphic to 0 in T, so H0 of A, which means this means homotopy equivalent okay, very good, very good. Okay, and then the strategy, again, representability. Or if you want, I mean, whenever I say representability, I could also say Yoneda. Like everything revolves around this Yoneda lemma and the Yoneda embedding. It's really a powerful tool. So what we have here, this cone is actually the cone of the identity between these DG modules, and there is a result that it's enough to prove. So it's enough like so to prove that this cone of this identity is homotopy equivalent to 0 as a DG module, and this is the same as saying that this identity of this cone is a co-boundary for some alpha cone. Sorry. Cone. Of degree -1. Okay, very good. Just to simplify notation, let me call M this. It actually, I mean, the argument actually works for a general DG module, but like, okay. So we have to find this like homotopy, if you want, this alpha, such that the differential of alpha is just the identity. And now, I mean, there is this like general hint, if you want, I can give you general hint. And this works in homological algebra in general, in homological algebra, which is what we are doing actually, homological algebra, but also in general in category theory, at least in this kind of category theory. In homological algebra, usually the most obvious choices would work. So, I mean, we need some alpha. So what is alpha? It's a morphism of degree -1. Now it's like we are working with concrete DG cones of DG modules. So we know what is the cone? Let's write it. Cone of the identity of M, its component is this. I mean, I actually forgot the reference to the objects. I mean, that of course it's like a DG module, so it's like a term-wise complex, but I mean, let me abuse notation even here and just forget about this the reference to the objects. So this and the differential, you know what is that, what it is. I mean, so the differential, it's essentially minus the differential of M minus this, and I mean, you have the identity, so this is the identity of this. Like this. This is the mapping cone explicitly. And then you want to define some alpha, which has to be degree minus 1, so be careful. Its component has to go from like let's wait. Oh yes, there's a typo in my notes. I will fix it, but it's okay. So that will go from here, which is the ith component of the cone, and then you go like 1 degree lower, so that will be mi plus mi minus 1. So like let's view it in matrix notation here. So like input, this is mi plus 1, mi, and like this is the input and this is the output. Okay, wait. Okay, mi minus 1. So you see, I mean, take the most obvious thing here that you can do with your data. With what you have, you don't have much, you have just identities, what you have. I mean, you can't do much from I plus 1 to I, so let's do 0, and I plus 1, I minus 1, even worse, 0, I minus 1, 0, but here, the input is mi, the output is mi, so you can put the identity of mi here. So let's write it maybe a little in a little nicer way. So 0, 0, 0, the identity. Okay, and then like this was the obvious choice. And then you have to check everything, so that with this definition you actually get a degree minus 1 morphism of the G modules. You have to check, of course, you have to check compatibilities with the. I have to check that it's a morphism of the G modules. Of course, it's okay. You can do it, and then you can check that indeed this. Have to check that indeed this holds. I will not do it because it's nothing really interesting. You can try it yourself if you really want, but I think the thing you should maybe remember from this proof is like the basic strategy is, as always, Yoneda. And then when you need to find this alpha, like you have this general like hint in homological algebra, you have some limited starting data, and with that data you make definitions and you do stuff. In the obvious possible way. I mean, there are not many choices, and like here, for example, for this alpha, the only thing was to put some identity here, and the rest we had no reason of doing nothing but of doing anything but just putting zeros, and this will work. So if you want, just check this, but yeah, this is okay for the first part, which was a non-trivial one. I mean, the second, like we need to embed f into some distinguished triangle, but I mean, we can just take the pre-triangle and view it and view it in H0 of A, our T. That's fine. And the third one, I mean, that's essentially by definition. Why? Well, how did I define distinguished triangles? Well, distinguished triangles, if you look at it, if you look at this, if you look at the way they are defined here, like the way they are defined is that any distinguished triangle is kind of isomorphic to a pretriangle. So like what you do here, fortunately composing isomorphisms also gives an isomorphism. So you get you get this one, you will view it as isomorphic to some pretriangle, and this one you will view it as isomorphic to some other pretriangle, and then the fact that you have an isomorphism here like tells you that, like, I mean, if this one is isomorphic to some pretriangle, then the other will have to, and if this one is isomorphic to some pretriangle, then the other will have to. Just take the inverses maybe of these maps here. I mean, this is not difficult. This is just coming from the way we define pretriangles. So there's not much to prove here. I mean, the non-trivial part was to checking that indeed the cones of identities were actually isomorphic to 0. So that, yeah, in the end you could, well, if you want to be very pedantic, why is this working? I mean, like, this is 0 in T, so what you can do is, like, you can take this, and then this, you have an isomorphism with 0, and here take this, yeah, and you compose, like, this map is the 0 map, and this map is the 0 map, and this is going to be commutative diagram. So in T, I mean, this is going to be also the 0 map in T, because this is isomorphic to 0. So, like, well, maybe I'm being too pedantic here. So in any case, it's done. It's okay. Oh, so good. Okay. So this was the first property. There is another one which is, like, probably the trickiest one. I will check today, and we'll see what is this about. But I mean, even if it's going to be a little trickier, the strategy is going to be the same as usual. So we will use representability, and at some point we will need to do some stuff, some homological algebra stuff, and you will need to make the obvious choices. Like, I think in some sense it's even more instructive if I didn't, if it would be even more instructive if I didn't tell you how to prove these, and I just gave some, like, more even more basic hints, and then tell you, well, try and do it yourself, because, like, it's really that way. I mean, these subjects, it's best learned when you try to do proofs yourselves, because the proofs are normally when you know how to what to do essentially, and basic strategies, then the proofs are actually kind of trivial. Maybe they're kind of tricky, they are, like, boring to write down, but they're kind of trivial. In any case, the second property, which I call TR2, is as follows. So we have let maybe let me write a little there. Let A, give some names. C, P, this is be a distinguished triangle. In T, of course, everything is in T. It is fixed from the beginning, and together with the pretriangulated digit category A. Okay. Then the sequence is so you do this: B, C, take J, A of 1, P, and here you put minus f of 1, some reasons why there's a minus here, some reasons I didn't really understand myself. So I mean, this like signs, as I said, are not very relevant conceptually, but have to be taken care of, unfortunately. You have this sequence and also this one, minus p minus 1. There's a little caveat here, I will tell you, and maybe you already see what thing is. These are distinguished triangles. I mean, as I said before, here we abuse notation. And like identified the C to this did we wait? Ah, yes, indeed, because that one, that would be C minus 1, then 1, and a this via the ISO of functors described before. Okay, I mean, so with this with these identifications, then of course, I mean, this p shifted by minus 1, as I said, p here would be from C minus 1 to A 1 minus 1, but then you view it as an identity, so also this, like, you identify it with, like, if you want, the real one composed with this. But I mean, let's think it's good for this purpose to think like of these isomorphisms as identities. And as I said, sometimes it's when you have natural isomorphisms, so isomorphisms of functors, then it's it's good to view them as like really identifications. Sometimes it's an abuse of notation, but it's sometimes more useful than not doing this. Okay, so how do you prove this? We prove the first one. I mean, the second, just to prove that this is a distinguished triangle, and the other one will be kind of similar, and I will not do this because, I mean, even the first one is kind of tricky from the technical point of view. So what we are going to do is that is a distinguished triangle, but like we can build some pretriangle in any case, which is this one. You take your thing here. Well, first of all, proof. I mean, we have this distinguished triangle, but we know that distinguished triangles are essentially up to isomorphism. They're coming from pretriangles. So, I mean, you can maybe accept that without loss of generality. We may assume that our given distinguished triangle is induced by a pretriangle. So, like, it's real the cone together, I mean the real cone together with its representability property, so it's universal property if you want. And what we're going to prove that we have a commutative diagram So that one, take this, and then you do the pre-triangle, but on this J, which, I mean, this J, if you remember, that came from some inclusion. No, first you do this, like above you take, that's what you have. And then this identity here, this J, but like below, you really take the cone of J. So you take an iterated cone, because if you want this is a map to a cone, and then you take the cone of this map to a cone. Like, and they are both pre-triangles. No, this one below is a pre-triangle, because it's like, by definition, this is pre-triangle, or comes from a pre-triangle, so it's distinguished. In T. And you want to prove that you have some isomorphism. Actually, commutative diagram will be in T, where W will be some isomorphism in T. Okay, so we want this, and well, how do you prove this? Again, representability strategy. Well, it's a little bit tricky. Plus unravel everything. In the framework of the G modules. Okay. So we need some concrete descriptions. Like, unfortunately, for example, you see this cone here. Like, what is that? It's the cone of this to this. But the cone, it's again a cone, so it's the cone to a cone. Yeah, you see it. Well, okay. So, like, you have to unravel everything, and you can actually see that, like, you can essentially identify this component. Like this is really just unraveling everything. Have this I plus 1 coming from this component, plus you will need some ith component, the ith component of this cone, but itself this ith component of this cone will be this I plus 1 plus this. So this is it. And I mean the differential, if you really like, if you view it as an identification, this one as kind of an identity, then like it's like this. Well, this is I plus 1 b, then have 0, 0, 0, minus this. I mean, this is just really writing everything down. It's very boring, but I mean, here you have the identity on this, and I mean, you can wonder why. The thing is that, I mean, you're taking the cone of this, J. With J, what is that? I mean, if you view it like in the DG, like if you apply the Yoneda embedding and you view it as the morphism of like from this to this is just the inclusion. It was just the inclusion onto the second component. And I mean, if you want, I mean, you see in matrix notation, this like this map here really is the inclusion of this to the second component of this. So, I mean, yes, it's have to think a little bit about it if you want, but it's like, and here you have the F, or at least the Yoneda image of this F. So you have this big differential, and you want, and when we define I want to define this W from like this. I mean that this one we identify with the shift of this, and this one we identify with this together with this differential. So in the end, for example, the ith component will be something like this. Have a shift here. I mean, I can understand maybe it's really just boring and complicated. I'm just doing this just once, and then it's the trickiest part today, and then things are going to be a little bit better, I hope. Okay. So what should I do? I mean, this has to be made so that has some hopes that this will kind of be commutative, at least in H0, but then what will I do? Like, as I said, again, kind of the obvious choices here. Like, you can put minus F with the I+1 component. Here, the second have the identity. There's nothing more to do. And like the other, can't do much, so it takes 0. I mean, this is it. And then you have to check everything. This is a morphing, this is closed, and degree 0. And now, of course, you have to test it with this, like, it's a map, it's a morphism of the G modules. You have to know, like, how to compute its differential. You have to use this differential, this matrix. It's going to be boring, but yeah, it's going to be quite boring, but it's going to be working out. And then what you do, like, have this W. We want it to be some isomorphism, but in H0. Then we look for if we want a homotopy inverse, and again, I mean, have to define something. Again, I call it this from this to this, and again I identify this with the shift of the DG module, and this with the, like, this, and this with this huge thing. And then again, this is going to be a matrix, and the ith component is going to be something like this. I+1, I+1, I, and then I+1. Okay, so what is that? What is this going to be? Well, not many choices here. Okay, so you have it, and then you have to prove everything. So like immediate, at least when you compose this way, there you go. There you have your, so that, and then want that when you take, now we are, like, I'm writing the cohomology classes, these are defined as like actual morphisms in the G modules. Now we're working with cohomology classes, and that there you want this to be some identity on this cone. And again, so explicitly alpha of degree -1 such that the alpha then is going to be the identity minus this thing. And again, I give you the solution, but again, this is the unique possible. We take, I mean, it's a big matrix because it's like from this, as I said always, I repeat, but it's the important thing. I mean, these computations are not really the important part. The important part is really to use representability and then make some, and then like you can handle it somehow, like identify with that, and then we can take like, again, you see that alpha I as matrix notation, it's like 0, 0, 0, 0, 0, 0, 0, 0, and here you put some identity. And then you see that everything works. So this is it. It's not really over. We need to check commutativity of the diagram. The diagram, which diagram? I mean, like this diagram. Yes, this diagram here. So thing is, here this square commutes essentially strictly. So the only thing is that we have to check the commutativity of this, and this will not hold strictly. But what you can do is to prove that actually it holds strictly when you look at the other way, when you use the other morphisms. So if you do this, let me see, if you do this, and you put it the Z morphism, then by definition, what is that? Sorry, P, yes, P. And like with that, you have strict commutativity. So this is really equal to this. But then, I mean, and this is inverse of this in H0. And then using this, you can see that, I mean, you have strict commutativity with this Z here, and this is the inverse, so you can prove that if you do this and this is the same as doing this and this because you can like use the commutativity of the other one to check it. So it works, in the end it works. And yes, the other one I will not do. The other one I will not do, and it's similar argument. You show that, for example, then you have this. I mean, you see that it's quite boring, but I mean the strategy will be the same. It's kind of a dual if you want this W here, not the same W, but I mean you get what you want. You get the point. Okay, then like you have to find some commutativity in a H0. Yeah, and this is it. I mean, you can check this, like, it's similar strategy, probably kind of boring too, but it works. I mean, so in the end, you see the result itself. Let's look at it again. So what you have, this is called sometimes rotation axiom. And it says that if you have a distinguished triangle, you can like rotate it on both sides, on both directions, and still get some distinguished triangles. So, like if you remember, like when you were dealing with pretriangles and the G modules, I call the thing like this sometimes the rotated pretriangle. So you see here that, like, now you have some like justification, if you want, for this, like, and if this is a distinguished triangle, then this is still a distinguished triangle, so it's kind of isomorphic to, again, a pretriangle. I mean, yeah, okay, fine. So this is it. That was the most boring part of today's lecture, I guess. And then finally there is the last thing, the last axiom, like kind of axiom we're going to prove. So now before I prove it, now you should know, I shouldn't even give you this definition. What is a morphism of distinguished triangles? So what is this? Well, you can imagine that you have two distinguished triangles. This. And a morphism will just be like you have some u, w, v and w. And here you put the u shifted by 1, and everything will be commutative. It is commutative diagram in T, where, I mean, of course, this map is induced from the one given here. Okay, so the last thing we are proving today is this proposition we called TR3. This is probably the easiest one, and to prove at least. So you start with some distinguished triangles. What am I writing here? No, sorry, that's wrong. A prime, B prime, C prime, A prime of 1. Oh, okay. Be distinguished triangles. Okay, in T, of course. In T. Okay. Moreover, let this be a commutative square. And then the result is that there exists a morphism between the, if you want, the wannabe combs, such that when you put everything together, this is a morphism of distinguished triangle. I mean, just a commutative diagram. Okay, good. Good, good, very good. Okay, how do you prove this? It's not too difficult, actually. Okay, so, I mean, what are distinguished triangles? They are things which are isomorphic to pretriangles, essentially. So, I mean, you see that, like, isomorphisms, you can compose them, it's like, you can compose everything, so it's not a problem if you change some object with some isomorphic one, in this context at least. So, without loss of generality, we may assume that the given distinguished triangles come from pretriangles. In A. And now, I mean, here, be careful. I mean, as I said, I'm abusing notation. I mean, when I'm looking at pretriangles in A, these are going to be kind of strict maps. We will need to work inside A for this proof. So you have this and this cone, the actual cone with the universal property. B prime, F prime, J prime, cone of F prime, A prime of 1, P prime. Good, okay. So, what we have by assumption is this. Now we have a U and V. I mean, here in the statement, okay. I lost contact. Okay, so in the statement here, the U and V were morphisms in T, but now we are putting ourselves actually in our DG category. So our U and V here, this is a little abuse of notation. We will maybe forgive me. This U and V are actual closed degree 0 morphisms, like these. UV closed degree 0 in A, but the assumption is that the square is commutative in T. So what does it mean to be commutative in T? It means it's commutative in H0 of A. So explicitly, it's this compatibility of cohomology classes, and explicitly, there is some H from A to B prime of degree -1, such that the differential is this difference. So this H is, if you want, witnesses that these two are like not equal, but their cohomology classes are equal. And this is an important point, actually. Okay. Okay, so what is again the strategy? I mean, in order to define your W here, what you will do, you apply the Yoneda embedding, you will define it between like the cones as DG modules using the representability, and then everything will work out. So how do you do this? You apply the Yoneda embedding everywhere. We look for a closed degree 0 morphism. The cone of the image of the unit embedding to the cone of the image of the unit embedding. So again, in components, what is this? We need this is what it is in components. Okay, good. So, and in matrix notation, I mean, you don't have much choices. I mean, we made a choice actually, and this will be an important thing to remark afterwards. But after we made this choice, like have your U, this, your V, just the images, I mean, through the unit embedding, and then you have your H. And then you prove everything, and then prove everything. So that it's closed of degree 0, and then that you have all the, it's like the right one which makes everything commute. And the good news is here that commutativity of this and this will actually hold strictly. So you will have to compute like this, and it will be by definition equal to this and this. And like also this and this, it will be equal, strictly equal to this and this. Like, so, I mean, by strictly equal, I mean really equal in the DG category, not just in the homotopy category. Okay. I will not do it. Try that yourself. I mean, but it's like now there are no more real ideas to share. So this is done. But there is an important remark, something to say, remark. This is very important. Important. Let me use some color. We can't expect uniqueness of this map, which completes the commutative square to a morphism of distinguished triangles. And like the point is that we made a choice. Like in this proof, we made a choice. You see, we chosen some H such that like the H was this, like this difference. A different choice of H could have brought us to a different choice of W. I mean, by different here, I mean even different in H0 of A. So you can choose a very different H such that still holds, and you will get some W, which will be even different when you look at it in the homotopy category. And actually, this is kind of a problem, because this says that, like, slogan, if you want, cones are not functorial in H0 of A. I mean, every time you have functoriality, you see there's some kind of uniqueness or some kind of well-definedness of some functor. I mean, normally I would try to define something which takes some map F, okay, into its map, into its cone. Like now I'm working in H0, and then I would like to say, well, I'm taking some commutative diagram in H0 to some unique morphism between the cones, and I don't have uniqueness at this level, and this is a very big problem of the homotopy category. Still, good news. Cones are functorial in the DG category and the caveat here, or if you want the idea, keep track of H. So if you instead of like looking at your starting data as just this commutative diagram in the homotopy category, you say that my starting data is a diagram here in your DG category, which is not strictly commutative, but it's like it commutes up to a choice, which is part of the data of some homotopy witnessing the difference of this and this. Then if my starting data is this plus this and this, then the morphism between the cones is actually unique, and the cone is actually functorial in this sense. So you see that if you want to have functorial cones, it's good to have DG categories, it's good to work in DG categories, and you will not expect it to work if you just work inside the homotopy category. Okay, so we are almost done for today, and like some final remarks. The ways I presented this material to you was like I start from a DG category, which is pretriangulated, actually strongly pretriangulated. Should tell you what not strongly pretriangulated means, but maybe you can imagine that maybe there are some DG categories which are quasi-equivalent to some strongly pretriangulated DG category, but they're not themselves strongly pretriangulated and still want to call them pretriangulated. Yeah, fair enough. In any case, for any purpose, it's good just to work with strongly pretriangulated. It's even better. And then we look at this, and this is endowed with a shift and distinguished triangles. But then, and satisfying properties I call TR1, TR2, TR3. There is also another one which I didn't tell you, which is called TR4. It's kind of even like the most difficult one would prove. It's like quite involved, and so we didn't do it. And it's also not much used, so well, whatever. Okay, but what I could do, and actually it's what historically was done, I could start from some k-linear category T, and then endow it with an additional so-called triangulated structure What is that? Triangulated structure is then a shift which is an equivalence in the sense that there is this inverse and a collection, an arbitrary collection actually, of distinguished triangles. Subject to axioms Now, the properties I proved in the case of a pretriangulated DG categories, and when looking to the homotopy category, now they are like given axiomatically. Again, this TR4, we didn't deal with it, but like have to include it in the definition. And that is what you call, a triangulated category. So triangulated category is actually T plus triangulated structure. I have to specify a structure. And the theorem, if you want, we actually kind of partially proved is that if A is a strongly pretriangulated DG category, then H0 of A endowed with the obvious, like I'm saying obvious, but it's like the one we actually discussed, triangulated structure, is a triangulated category. And the proof is like you define this triangulated structure as we've done, and you prove tier 1, tier 2, tier 3, which we've essentially done, and also tier 4, which we haven't done, but like, I mean, as an exercise, you can look it up yourself, and if you really want to, you can try and prove it. I never tried myself. I get that like it's not something which is going to be really difficult, but it's going to be quite complicated. So maybe like if you really feel like it some point in your life, then you can try and do it. But like I think that I gave you at least I gave you the like I've told you enough about like this kind of like strategies of like you do representability, you work within the DG modules, and on DG modules there are kind of complexes, and there you can do everything explicitly, and if you can do everything explicitly, it's just like homological algebra and computations and differential and stuff, and like it's not really difficult, it's just a little bit tricky sometimes. Okay, then I can say something more just from a philosophical point of view. I mean, as I said, historically, first you had triangulated categories. Well, let's say that actually in the very beginning you had derived categories, and almost immediately they were understood as triangulated categories. Derived categories, like kind of the ones we've seen, like here of rings, even of schemes. For if you really want even more generality, of abelian categories in general. I mean, we've dealt essentially with this one. But you can imagine that like have rings, then you glue rings, you have schemes, you also have the other category of schemes, and algebraic geometers really like them, and they like to do stuff with them. And then you have these triangulated categories, and then the issue was like no functorial cons, and that was kind of clear. So in order to, sometimes you really need the functorial cons, and then people came up with this notion of pretriangulated DG category. So historically, this was the path So pretriangulated DG categories actually came later than like the triangulated categories and derived categories, but like in this course we've dealt with them like from the very beginning, and so in this course we've done the other way around, so like this. Like there are still some questions that can be interesting. Like, for example, you can ask, like, given T triangulated, some triangulated structure, is there a pretriangulated such that H0 of A is kind of at least equivalent to T, is such a unique, let's say up to quasi-equivalence at least. Well, I mean, for the first question, I mean, by the way, you call this a DG enhancement somehow. Sometimes, if you want to look at, if you want to look this up on the internet, you find some literature. I mean, it turns out that this first question is easier than the second one. So, I mean, essentially, in most cases, at least for derived categories, you can always find some DG enhancement. So it's okay. There are some problems when you go like to something more topological. If you go to spectra, then you have to be, then you may not be able to find some DG enhancement, and you'll be able to find some more general, even more general kind of enhancement, which are called like infinity stable infinity categories, or also spectral categories, or even things like this, also stable derivators. I mean, these are just words, but then maybe you want to look them up and see what's happening there. Like, this second problem is actually more difficult, and this is like active research still now, I guess. So like you would be able, I mean, in the best case, then you ask that you would like that, like, your triangulated structure somehow uniquely determines like the DG enhancement. So then you have just a unique DG enhancement, and many results have been proven, and there's still something to be done, I guess. And like, even for categories, for sure there are things to be understood, and like you can think about as like research questions, not maybe also for categories, but also for functors. There is this, you can ask these questions. We didn't deal with them, but you can ask, like, you can have this notion of triangulated functor between triangulated categories, and you can ask if it comes from something between DG enhancements. Even when you have unique DG enhancements, then maybe it could happen that you don't have just a unique lift of your given triangulated functors. I mean, these are questions that people are working on. So, I mean, if you like this topic, then you can ask me, and then I can tell you more on this kind of, and point you to literature and things to read, and even, like, I don't know, even tell you something more. But for the purpose of this lecture, well, essentially over. And like, as I said, the thing is, the triangulated categories, like homotopy categories of DG categories, thing is that you don't have functorial cones, but still, it's worth saying that, like, even just working within triangulated categories, there's a lot of things one can do, of lots of constructions, lot of mathematics, just with using the the axiomatic approach. So you give the category with a triangulated structure, and these axioms are kind of nice to use. You can do many computations with them, and maybe an approach would be like, when you need the functorial cones, you invoke some enhancement at the DG level. And this is a possible approach. Another approach, on the other hand, would be, of course, you start from DG categories with DG categories from the very beginning, and you work just with DG categories, and then this tier 2, tier 1, tier 2, tier 3, tier 4, they're just properties that are useful
for computations, but I mean, in your head, the main objects will still be pretriangulated DG categories, or even some more complicated and general notions of this kind of higher enhancements for triangulated categories. For example, I don't know, as I told you, pre-stable infinity categories. There are also spectral categories. There are stable derivators. There are things like this. And yeah, I think both approaches, I mean, the one you like more, that is the one you will choose. And like, I'm quite agnostic on your choice. I mean, you can, if you're happier with one approach or the other, then go for it, and it will be okay. Okay, fine. This is everything for today. I think I've spoken for even more than 1 hour and a half. I mean, fair enough. It's a recording, so you will have it, and you can like skip if you need. And we'll see each other live, hopefully, next month. So